from here. So is anyone able to
Yep.
start the recording?
I started it.
Oh, it's being, is it?
See the red button up there?
Yeah. Okay, so maybe it's automatically recorded. Okay. So if it is, that's great. Okay, so geez. Okay, so okay, it means someone new is. I don't know how to switch off this loudspeaker. So from
on the bottom right, like turn the slider down to like a 20.
the bottom on the right.
Further down, like see the windows. Extron scale ID.
So
Bottom right. Bottom.
Bottom right. Okay.
Pause this thing. Just open click on the sphere.
Yeah.
And just slide it down to 20%.
I want. Okay. I will do it. Come on.
Just click on the Extron. Yeah. No.
Once again. Jeez. Okay. Is it any better? Okay, I will. In that way, I won't hear the guys from. Okay, so. Okay. Technical problems in the very beginning, my favorite. Okay, I'm going to use some slides prepared by Professor Orzechowski, just not to interrupt his way of conducting this series of lectures. So please forgive me if I'm sometimes puzzled by what's on the slides. I'm seeing them with you. Okay. Let me share. Probably I should share the slides. Can I see them? Not really.
I just share the whole screen.
Yes, probably I will just share the whole screen and I will stop it. Okay, probably you should see everything correctly. Okay, so the subject of today's lecture is computer-aided analysis. And the outline of the presentation is computer-aided analysis of mechanical systems. Then I will talk something about vectors and matrices, and having this, we will go to kinematic analysis. The lecture or the slides are based on famous book by Pavlis Nikravesh. It's an old book, but very nice. And if you have a chance to read it, just do it because it explains the multi-body dynamics in a very friendly manner. So you just read, you learn, and out of the sudden you are an expert in multi-body dynamics. Very good book indeed. Of course, there are other equally good books as well. Let's move. Few words about nomenclature, about notation used across this lecture, I think. So matrices are usually boldface and uppercase letters. So if we see something which is capital letter and boldface, it's usually a matrix. Several rows, several columns. Vectors are special kinds of matrices that is one column. Matrix with one column could be called a vector in an algebraic sense, of course. And those vectors will be denoted by lowercase letters and boldface as well. And finally, we have scalars, just numbers. So scalars will be written without boldface and with italics, usually. Okay, if we transpose a column vector that it is a row vector and zero, boldface zero is zero matrix of appropriate dimensions. By the way, can you see my pointer here? Yeah, that's nice because probably I will point to a few different things. Okay, what is computer-aided analysis? Well, the name is quite self-explanatory, in fact. So we use computer to analyze some reality. The important point is that multibody dynamics is an analysis which is usually conducted at the very beginning of the design process, when we are going to make crucial decisions. What should be the kinematic structure of our mechanism? How long distances between crucial points of this mechanism should be? Will this mechanism work as we expect, or something should be redesigned? So usually we use multibody dynamics at the very beginning of this design process, just to learn something about the mechanical stuff that we are trying to create. Well, sometimes this computer-aided analysis is also used at the very end of the design process, when we are trying to improve, to optimize something. In that case, usually we have both a complicated multi-body model and a real system that we can test in some kind of testing. And having this, we can adjust model to correctly mimic the reality. So we can validate model, make sure that the model is responding as the real system is responding. And having this very accurate model verified by testing the real mechanism, we can now start an optimization. We can answer the question, what if we move something, if we deduct some mass from here, or if we change the stiffness of a spring, how the model will react. And by this, we can improve our design. We can test a lot of virtual prototypes simply, instead of building the real ones. Well, at some point, we need to create another prototype, but this modeling can be very helpful, firstly, at the very beginning, when deciding how our mechanism should look like, more or less, and then at the very end part of the process, when we are trying to improve already existing mechanisms. Okay, so going back to the slide, computer-aided analysis allows the engineer to simulate the behavior of a product and modify its design before actual production, before building, or instead of building another prototype. So in brief, the same message is here. And in the mechanical engineering, well, we have different types of structures. We have typical structures which are unmovable, like bridges, buildings. Okay, they move, but they move very slightly. Okay, then deflect, they do something like this. This is the area of structural analysis. But in the mechanical engineering, we also have simple mechanisms. So systems of complicated kinematics, composed of a lot of moving bodies connected via different joints, subjected to different forces. So systems that move. And this is the object of study for multi-body mechanical, for multi-body dynamics. So we are analyzing systems that are built of many different parts, and those parts move one with respect to another. Okay, and here are some examples of multi-body systems. So multi-body system is a collection of bodies or links in which some or all the bodies can move relative to another. And here is the very simple 1 degree of freedom, just pendulum. Everybody knows this very simple mechanism. Well, the closed loop mechanism, like 4-bar mechanism here, are a bit more complicated. 4-bar mechanism is a very, very popular mechanism. If you look around, you'll probably see a 4-bar mechanism here. Yes, it's right there on the door. You see? The mechanism that closes the door. It's a 4-bar mechanism. So it's everywhere, the very popular mechanism. parts of this mechanism have special names like crank, connecting rod or coupler, and the follower or rocker right here. Another very common mechanism is a slider crank mechanism, where any piston engine uses this kind of mechanism. So mechanisms are everywhere. Those here are relatively simple, but we have a much more complicated mechanism all around us. A vehicle is a mechanical system, quite complicated. An airplane, everything that moves, excavator, lift in this building. So quite a lot mechanical systems are in our surroundings. So this is an abstract picture showing a multi-body system and explaining what is crucial and what is less important here. So a mechanical system can be represented schematically as a multi-body system, provided that there are really some bodies. The shapes of bodies, as you can see here, are quite imaginary. They are usually not so important. Of course, in fact, the shape decides of the mass distribution along the body. But I mean, the details here, if you create a multi-body model, usually you do not care for some details like rounding the corners, like drilling holes for something. The geometrical representation is deeply simplified. Why? Because this geometry is not reflected in the equations of motion that describe the multi-body system. As long as we stick to rigid body assumption, the shapes are not so important. What is important is listed here. So connectivity of the bodies, how the bodies are connected, how many joints, which kind of joints, is it revolute joints like here, or cylindrical joint like here, or universal joint right here, revolute, translational. The most popular joints are missing in this picture, but in the technical realizations of mechanism, they are very, very popular. So connectivity of the bodies, the inertial characteristic. Okay, we can neglect some details of our shape of the rigid body, but we should know where is the center of mass, what is the inertia tensor. Otherwise, our equations of motion would not be precise enough. So inertial characteristics are important. Well, type and location of the joints. It's not sufficient to know that there is a cylindrical joint. We also need to know where exactly is this joint, where is this line of sliding and rotation. Okay, so the geometry of kinematic pairs in terms of where this pair is located, how the axis is oriented, and so on, this should be known quite precisely. What else is important is the forces acting on the mechanism. That can be external forces shown here, or they can be internal forces like some springs between two elements of our mechanical systems. If you are analyzing, I don't know, a chassis of a car, you've got springs, dampers, and you need to know the characteristics of these elements. Otherwise, your model will be not precise enough. Okay, so we go through radical simplifications. We do not have spent time to draw very exact shape of our mechanism. We can just draw something like this, but the point is we should more or less know where is the center of mass, what is the inertia tensor, and distances from like location of this universal joint, location of this cylindrical joint should be known. Okay, let's move to the next slide. Well, probably you know that part of physics is called mechanics, and mechanics deals with motion, time, and forces, and masses as well. Traditionally, it's divided into statics and dynamics. Static is very important, especially for the structural engineering, for buildings, bridges, roads, and this kind of stuff. In when we deal with mechanism, dynamics is also very important, or even more important, because usually the largest loads are due to dynamics, not to statics. Okay, so we have to study everything here, and especially motion. Well, there are two ways of studying motion. Dynamics is everything. It's motion, forces, masses, everything that contributes to the physics. But we can take just motion. If we are dealing with kinematics, we just deal with geometry and time. So we put aside the reasons for motion, how this motion is created. So we neglect masses, we neglect forces. In kinematics, there is just geometry and time, and no other physical quantities exist. Then we switch to dynamics and we take care about the reasons for motion, why something moves, why something accelerates. Due to Newton's law, it's obvious that motion or acceleration is a result of force, and mass is also important here. So dynamics takes all those mechanical quantities together. Why we deal so much with kinematics? Probably because in the multibody dynamics modeling, the kinematic part is the most difficult. So once we are done with kinematics, we can easily go to dynamics, and this part, especially in the very beginning, in the rigid body modeling of ideal joints, the dynamic part is quite easy when compared to kinematics. Okay, the last sentence here is that to analyze motion, we must make some simplifications. Again, it should be quite obvious for you that model is an approximation of the reality. So we made some assumptions for sure, and we made some simplifications. In the case of this introductory course of multi-body dynamics, there were two very important simplifications and assumptions. I don't know if this is, well, assumption is a simplification. So the first thing is that we are trying to stay with so-called rigid bodies. So we usually ignore deflections of the individual parts. If we look at the mechanism, of course, every part deflects, changes its shape, but it's a very small change when compared to the whole motion of a mechanism. If we go back to this slider crank mechanism like here. Of course, every part of this mechanism somehow deflects, changes its shape, but it's very, very small change with respect to the whole motion. So the first simplifying assumption is let's treat all moving parts as rigid. It is parts that do not change its shape during motion. Okay, they move, they change position, change orientation, but shape of the rigid body remains unchanged. The other important simplification is that joints are ideal, so we neglect friction. This is important in the dynamics. If joints are ideal, no friction, then the calculations are much easier. It's easier to go forward. Of course, all of those assumptions can be weakened. So we taking a next step, we can model a multi-body systems which are not composed of rigid bodies. We can introduce flexibility and combine flexibility of parts with large rigid body motion of those parts. It's doable. Of course, it's doable to put some friction model into joint and to model this. Yes. Okay. I don't know if the guys on the other side could hear you. So the question is, if we add to our model flexibility and friction, how much, to what extent it improves the model? Yes. Well, it depends, as always. It depends how those phenomena are important. Okay, so well, let's think about a helicopter. Okay, and there is a very complicated mechanism that moves blades. When helicopter works, the blades are moving all the time. So the mechanism itself maybe deflects, but deflections of the mechanism could be negligible if we allow for deflecting them. Not much will change, but the blades itself, where it's a large blade with huge mass and deflection is large. If we neglect this, probably we introduce a huge error. So it always depends. For some mechanisms which are well lubricated, which are using good bearings, whether we address friction or not, it's not important. But for in many cases, friction is very important if you want to model a control process of some hydraulic systems and you neglect friction, you probably will end up nowhere. So friction is a very difficult phenomenon in modeling, but for some systems, you cannot neglect it. Well, there are systems there in which friction is the crucial part of the system itself. Okay, so some locking mechanisms or so on. Without friction, the model is useless, totally useless. So the answer is it depends. For some models, neglecting those phenomena makes the model completely useless. For some simple systems, if we add some more reality, we will see small differences, so which could be easily neglected, in fact. Did I answer the question? Okay, thank you. Okay, so let's move on. We have seen this slide and this as well. Okay, now some equations, finally. Okay. We quite often need to analyze motion of our system. This is a simple example of slider crank mechanism. And we are interested in finding velocity of point B here, having the dimensions of the mechanism. So OA, it's from here to there, the distance is A. From here to there, the distance is B. Okay. And probably phi, this angle here is given. In this precise moment, the angle here is 30 degrees. We know dimension of this mechanism. We are asking where is point B, and it's probably revealed on the next slide. We know the angular velocity phi dot is known. Okay, so we will be asking what is the instantaneous velocity of point B? Well, it's a valid question if you want to study thermodynamics of compression gas in the cylinder. You need to know how this mechanism behaves. So this is an example. I was browsing the slides. I got them yesterday, so they are new to me as well. So I was browsing through these slides. So I noticed that this is an example showing how to do it without any structure in our way of tackling this problem. So if you see at details that there are something like this angle is measured in the one direction, the other in the other direction, yes? Omega vector is again pointed this way. So there is no systematic approach here because the mechanism is very simple. The key point in multibody dynamics modeling is using a systematic approach. But let's start with this not very systematized example to show what's how the multibody dynamics is built. Okay, so we start with very simple geometry right here. If we take A multiplied by cosine phi, it means that we take this element from O to A and we just project it onto X axis here. The other part, B times cosine phi, is projecting this AB part on X. And all together, D, it's not shown here, but D is the distance from O to B. Okay, so one set of equations, one equation is quite easy to create. The other equation here is just projecting on vertical axis. So we take A and multiply it by sine phi. So it's projection of point A onto the y axis minus, go down this time, distance from A to B, this segment from A to B projected on y, all together is 0. So we go up, we go down, and we are at the 0 level. Why those equations, which happen to be called constraint equations, are important? Well, as you can see, we've got a mechanism. How many degrees of freedom does this mechanism possess? Just one, yes? So if we say how crank is located, we know everything else. Okay, and what we have here is phi, theta, d. We've got 3 coordinates here and just 1 degree of freedom. It means that we cannot choose independently all 3 coordinates. If we decide that phi is 30 degrees, well, we must choose the other coordinates accordingly. So those constraints equations show what are the dependencies between coordinates used to describe this system. So it means that theta here, d, and theta here must be selected so that those 2 equations are fulfilled. Otherwise, our coordinates would not express this system properly. Yes, it will be disassembled, basically. Okay, so having this phi equal 30 degrees, we should simply solve this set of 2 nonlinear equations to obtain the values of theta and d. Equations are quite simple. I hope there is no need to go into details how it was solved, because it's quite easy to achieve this. So at the position level, now after solving those equations, we know everything. At the time instant that is depicted in the picture, phi is 30 degrees, theta is 14 and something degrees, and d is 0.28 meter. Now we know that phi dot equals something. The question is, what is d dot? How to find this? Any idea? We know not, we are analyzing the particular instant of time shown in this picture here, and we know everything. We know the instantaneous values of our coordinates here. And we also know that phi dot is, I don't know, 1 radian per second or something like this. It's revealed on the here. It's minus 1 radian per second. Okay, so, and we are interested in how fast point B moves. What is the velocity of point B? How to proceed, how to learn, how to find D dot.
Basically, you change it up to the equation of motion.
Well, yes, equations. There is a problem with the term equations of motion. Okay, because as I said, we can study kinematics, we can study dynamics, and usually term equations of motion in multibody hemisphere, let's say, is reserved from equations that combine forces, masses, and accelerations. Now we are dealing just with kinematics, with geometry and time. Well, basically what we need to know is d dot. So how to proceed from positions to velocities. Exactly. What we do, we just take derivative. Those two equations, so those two constant equations must be valid at any time. Okay, so, and all functions here like phi, theta, d are functions of time. So if we formally take derivative with respect to time, we will see how those constraints are reflected at the velocity level. So this is the next slide here. We take derivative. It's not awfully difficult. The derivative of cosine is minus sine time derivative on what's inside. So it's exactly this, phi dot sine phi. Yes, and we take total derivatives with respect to time. Dot means derivative. You know it for sure. Derivative with respect to it. So those are constraints equations at the velocity level. Mind that in the previous slide, we managed to solve the position level constraints. So all those coordinates without dots, like phi here, oh, d is missing here, but theta here, they are simply known. The only unknown quantities are those quantities with dots, except for that phi dot is given. So in fact, we've got given phi dot and theta dot and d dot unknown. The nice thing is, if you look carefully at those constant equations at velocity level, you will see that equations with respect to velocities are linear. You see? In the previous slide, we've got sines, cosines, apparently non-linear functions to solve, to calculate theta and d. Now, all coefficients next to theta dot, d dot are known. Okay? And there are just theta dot and d dot. So those equations are linear with respect to unknowns. So they are extremely easy to solve. And this is the general rule. kinematics is very complicated at position level, especially complicated when we deal with three-dimensional systems due to some problems with parameterizing orientation. But once we are done with position level, we go to velocity level, and it appears that we end up with linear equations, the easiest to solve. We will not go to the acceleration level, but if we do the same again, if we differentiate velocities to see accelerations, we will see linear equations with respect to acceleration. So kinematics is very, very complicated, but only at the position level. Of course, then this process of taking derivatives, it may be tedious. It depends on coordinates that you are using. Sometimes it's very complicated. You need to use some recursive equations. Sometimes you can easily take some derivatives. It depends, in fact, on the selection of coordinates. I'm going to talk about this today. But generally, you end up with linear set of equations, and so you can solve it. And this was solved here. So for this given theta dot, phi dot, we obtain theta dot equals something, d dot equals something, and we have just solved the problem. What is the velocity of point B when the position is shown in figure, and we know the velocity? We could do the same with acceleration as well. By the way, it's quite common that in kinematics we go up to acceleration level. Why we do so? Why don't we end at the velocity? Why we usually do not go farther than the second derivative? What is your guess? Why we are studying kinematics usually up to the accelerations?
Dan, how you mean that?
Well, I mean, in the previous slide, this is the kinematic problem at the position level. We are studying positions, okay? Then we moved to velocities. We are studying velocities, and it's just an information from me that usually in multibody dynamics, you go one step further, you differentiate those equations, and you study acceleration. It's because you know the phi angle, phi dot, phi double dot. Okay? And usually we do not go any further, but we insist on studying kinematics of the position, velocity, and acceleration level. Why we usually end up at accelerations? Well, this kind of equations you can differentiate and differentiate endlessly. You can take the third, fourth derivative.
The derivative has no more meaning for us.
Yeah, usually that's right. Okay. How about your guess? It has, if we study impact or something like this, but usually the physical meaning of acceleration is crucial. Why is that? Exactly. It's due to the Newton law. It happens that Newton law is formulated at the acceleration level. That's how the world is organized. It's not Newton to blame. He just discovered this. But the problem is that the motion, the motion itself, which is kinematics, relates to the reasons for motion, like forces and masses, at the acceleration level. So to effectively deal with dynamics, which is our aim at some point, we need to study kinematics up to acceleration level, because that's the level at which we can include masses and forces and formulate equations of motion. Okay, so, well, it's good to know, because usually kinematic part takes a lot of part of the course, and people not always know why are we dealing with those accelerations, because differentiation is quite complicated, quite tedious, and why do we bother? Well, there is a reason. There is a reason, Newton law, basically. Okay, let me move. In order not to start from scratch for every single mechanism, we can think about computerizing some calculations. And we can do it in two different ways. We can try to create a general multibody code, a program that automatically creates, solves equations, and provides us with results. A program that can analyze virtually any mechanism. The other option is not to use a general purpose program, but a program which is specially designed for our particular mechanism. Well, in terms of efficiency, of course, if we derive equations for one particular mechanism, we can do it in a much more efficient way, especially the final code would be more effective. Sometimes we have to do it if we want to analyze a system in a real time. For control purposes, we sometimes need to know what is the behavior, to calculate the reality faster than the reality occurs. It is very helpful to provide proper control for systems like robots or other systems like, I don't know, maneuvering aircraft or something like this. So efficiency sometimes is crucial, and we have to analyze mechanisms as efficiently as it is possible. On the other hand, if we would try to create a program for every single mechanism from almost scratch, well, we will do nothing during our life as engineers, yes, because those mechanisms are endless. So there is a need for general purpose programs, and it is possible to do so. Something like this, there are several programs like that you are just drawing a system, link, another link, you are declaring here is a revolute joint, there is a translational joint, here we've got universal joint, there is a force like here. And then you press the button play and you see how it moves. The nice thing, it moves according to the physics. It's a valid model, but the difficult part, like analyzing the structure, writing down equations, solving them, is done automatically. And multibody dynamics courses are usually focused on this, how to create a program that is able to automatically analyze the system. Okay, of course, we need to provide some data for those programs. So let's go through this slide. General purpose program can analyze a variety of mechanisms. Yes, that's why it is a general purpose program. The input for the program must include the number of bodies. Well, yes, you need to know something about the mechanism. Connectivity, it means which body with which body is connected and how it is connected. What is the joint, joint type? We need to know forces. If there are springs, dampers, we need to know their characteristics. If there are external forces, we need to know them to see how this works. And of course, geometry should be known, but as I told you before, not the whole geometry. The geometry of crucial points like where joints are located, where centers of mass are located, That's it. The other geometrical features are not so important at this stage of modeling. And then we can use a program. You can buy the kind of programs that automatically generate and solve equation. All you have to do is provide just to draw a mechanism and declare where are joints, where are forces, where are springs, where are dampers, and so on. Okay, and computational efficiency depends on many things, of skills of the programmers, for example, but also it depends on choice of coordinates. There are some coordinates that are better for multi-body dynamics than other coordinates. And the next part of this lecture will be devoted to the choice of coordinates. How about 5-minute break? Just to give a room for just moving around. Otherwise, you will fall asleep, probably, and I will as well. Okay, so it's 10:02. Let's meet at 10:10, okay? In 7 minutes. Okay. Is this course devoted to the multi-body dynamics, or it's just more general, like
General math programming. I'm not sure what actually causes it all.
So this is just a small introduction to okay.
Multibody dynamics is currently delegated to the simulation of a mechatronic machine and the follow-up course. It's like mostly there's a whole explanation of how to do it and then like lump mass, how to connect it, and then simulate this in MATLAB. And this basically is somewhat similar, but that little bit different explanation.
Okay, but this course interface seems to be one of these introductory courses, yes, at the very beginning.
No, this is the end.
Oh,
It's a little bit confusing to me.
okay, so well, I was assuming that it's okay. So sorry for asking stupid questions.
No, it's not stupid. I think the problem is they have this. For instance, this could be a little more specific. The problem is they also have like Erasmus students and other students which come in and take this course immediately. But I feel like this university is a bit too hesitant to make like requirements that you already have taken other courses. Because this one should also have like requirement you have taken this in this course already, so you can go more in depth. But like some other courses have like the same problem that they basically need to always start from the very beginning and then rattle down.
Okay, so introduction part 7.
Yeah.
Very good. Yeah. But it's usually the problem that the lecturers do not know what exactly was said in the other lecture a year before for the students.
I mean, the previous course, we actually used, I think, simulating MATLAB, and we did the whole simulating things of form, like all the system. So like the universal system to input multi-bodies, like
Well, this
machines we've already used that.
there is a simile plugin for multi-body dynamics. Well, there are better, more user-friendly programs than this.
That's the one we use, but yeah, it's kind of upside down. We did that first, and now we get the introduction to it.
Yes, but so it's like with puzzles. At some moment you got the whole picture.
Exactly.
The problem is if introduction comes after the details, but
It seems to favor like people who actually try to do this in like 1 year. Basically, they can take like 60 credits worth of courses in 1 semester, and then basically be done with the master in 1 year. It feels like it's a little bit like pivoted towards that. A little bit weird, but like I'm not sure like what is the best option, like to not do this or to do this. It's different.
always a question if you have a fixed program. You start with this, you go there, and well, there is not many elective courses. That's with not much flexibility in studying. Otherwise, well, sometimes students take a course because it nicely fit just to their schedule. Because it's on Monday between 12 and 2 o'clock, which is perfect. And you earn some credits just because of it.
So in Germany, like in Germany, the bachelor at least had like only like 10 or 5 like choosable credits from like 180 credits I had to do.
Mm-hmm.
Like in comparison to this, it was like much more streamlined. Basically, you had to do this, and then like in this semester you have to do this, and this is like the requirements. You have to do like all of this before you can move on to the other courses. It's like constantly moving on. Like basically, you can't do the other stuff before you have done the other stuff. And it's like much more strict in that regard.
Mm-hmm. Good.
And one of them was actually university in Göttingen. You can actually feel like basically, I think most brutal was math. I like tried to use the university math, not the computer science math they also gave us. And that one was just, yeah, I like, you probably had this all in school. I'm not going to explain it. We're just going to like go at like 2 times speed through all of the math things and change back to like computer science math afterwards. Finding like the brutality between some of the courses.
That's right. Some courses are going very slowly, and the students have to, well, have a chance to really learn, and some go very fast. And if you want to follow it, it means that after 2 hours in classroom, we need 6 hours in library just to go again through this material.
Well, I think in the German university where I was in, it was also mostly the course because that was like in the first year, the first courses they take, all of them extremely full. I mean, it's German, it's like, so they basically use this as a chance to just rattle down as many people as possible. Basically, they like say, yeah, 50% of the people who start actually go to the end or even less. And that's basically one of the reasons why.
Well, it happens at the introductory year in Warsaw that we have the same. About 30 or more percent of students just give up. Well,
It's the first course, I mean, the first year is the worst one in bachelor because it's just. But however, that one was especially like brutal in some cases. I once myself like the math, the homework you had to do. And it took me like 6 to 8 hours, and it was like one of the other courses. And also a lot of people like who were in university stayed at the room, like where you can submit it overnight, and basically slept there after they just passed it in like in the morning. And
students are. Okay, shall we resume? I think so. Okay, welcome back. Slide number 12. So we are more or less in time because I've got about 40 slides for 3 hours. So. Okay. Choice of coordinates. Choice of coordinates is very important because with some coordinates you have a bit more effective codes than with other coordinates. On the other side, there are some coordinates which are not so ineffective, but they are very easy to implement. I will show it to you that some set of coordinates is very useful for multi-body dynamics. It's not the only choice, but if you want to write from scratch your multi-body code, you should take a specific set of coordinates to make your life easier. If you want to spend a lot of time on creating code for maybe a bit more efficient coordinates, well, you can select the other type of coordinates. So let's go through some examples of choice of coordinates. Let's have a look at the 4-bar mechanism again. So let's start with generalized coordinates or minimum coordinates. So if we've got a mechanism that has 1 degree of freedom, as this has, theoretically, we could just use 1 coordinate. Basically, if I know phi angle here, the set of coordinates is just phi angle here. Well, I can tell what's going on with the rest of the mechanism. So the position of the mechanism is fully described by setting proper value of angle phi. And the other important angles, like angles in all other joints, can be calculated as functions of phi. Is it easy? Well, it's not rocket science, of course, here, but the mechanism is not very nice to analyze. If I ask about θ2, it takes some time to say what is θ2 for a given phi. Okay, somebody did it. Well, it's like this. It's probably a high school geometry, some theorems, some triangles analyzed, and so on. You can do this. Yes, you can express everything in terms of phi, then calculate auxiliary values like θ1, θ2, and θ3, and you can solve it. But looking at this example, we can say it's not extremely easy to do so. And so maybe we should choose another coordinates, not necessarily minimum coordinates. So let's have a look at relative coordinates. Like here, we can measure relative angle is in this joint, relative angle in this joint, and relative angle is in this joint, and take those 3 angles as our coordinates. By the way, mind something like this, that phi2, phi3, phi1, they are all measured with respect to the, let's say, global x-axis here. Okay? Is it doable in 3-dimensional system? Not really, or not at all. Not at all. So this is a very nice simplification, but valid only in planar systems. If you are going to analyze a robot or something which is 3-dimensional, well, that's not the proper way to measure relative coordinates. So this particular picture shows very special case, very useful, and in planar system we use it often, but in general, the idea of relative coordinates is that you measure angle or displacement with respect to the neighboring body. This joint B is created by part 1 and part 2. And coordinate phi2 should measure relative motion of part 2 with respect to part 1 in the, let's say, canonical approach to relative coordinates. Okay, can we choose those coordinates independently? No, because if we do so, if we just put random values here, most probably the kinematic joint here at D would not survive. We would have some open ring serial structure, open kinematic link, not connected in the back to the bases. Okay, so we need to formulate some constraint equations. By the way, another thing that you should notice here is that when we decide to use relative coordinates, doesn't matter those special like here or those general canonical, which means the next body with respect to the previous one. You see, there is no coordinate here around D. So we've got 4 revolute joints, but only 3 revolute joints have some coordinates associated. Okay? What we mentally did, we just cut the loop here and D. If we cut loop at D, we can independently choose those coordinates phi1, phi2, and phi3. And now we are producing, we should create some constraints equations that express existence of this joint D here. So we must constrain our coordinates so that all agrees with within this mechanism. So let's have a look at the next slide. And what we see here, it means that, well, R, D, and S are probably lengths of those links here. So we go like this: R cosine phi, this is R cosine phi, we project it on X, plus D cosine phi 2, we project the coupler here on X. S, which is probably the rocker here, cosine phi, we project this segment on on axis X. L is the distance between A and D. So if we subtract L here, we end up right there. So we go like this. We go around the whole loop and we project everything on X axis. We end up with 0. Okay. The same loop, we go up to the right, down, back to A. We project all this path on Y, and we end up with 0. So those are loop closing equations, constraint equations. And we've got 2 equations with 3 coordinates, which leaves us 1 degree of freedom. We can choose one of those coordinates and use those equations to calculate the other 2. Okay, so if we take number of coordinates and minus number of constraints, we should obtain the number of degrees of freedom, the mobility of the system. So if we decide that phi1 is known, we can calculate phi2, and that's done. By the way, if we were using the proper or canonical relative coordinates, so it means coordinates measured with respect to the previous body, how much different those equations would be? Well, I have no idea how to use a whiteboard here for guys on the other side of the internet, but basically, well, I will use it. I don't know. Probably they will see nothing. Well, and the thing is, if we measure our coordinates in that way, this would be phi1, this would be phi2, and this would be phi3. Okay. Then in our constraint equations, it's like R cosine phi 1, nothing changed. But then plus it is this, yeah. Cosine, what should go here? Sum of those phi 1 plus phi 2. See? We rotate up to here, then we add here. This is the final angle of rotation of this. Yes, so that's how it looks like. Plus it would be S cosine and sum of the 3. Phi 1 plus phi 2 plus phi. Okay, so, and the rest is the same. I'm showing it because this canonical form would also be valid in three-dimensional systems. This kind of measuring coordinates is restricted to planar system, so not very general. Okay. So we've got moderately, or rather quite complicated equations right here, but still it's much easier to create those equations than equations for general or minimal coordinates, yes? To derive this, it would take a lot of time. Here, it's much easier. So relative coordinates, often used in multibody dynamics, but not the most popular, basically due to two reasons. The first reason is that those equations are quite complicated. If the kinematic chain is longer, the equation becomes longer. We have much more bodies to visit when we are traveling around the loop to create the loop closing equation. The other not very nice feature is that we associate coordinate here and here and here and here not. Okay, it's not an obvious choice where to cut the loop. Yes, why not at C? Why not at B? Why not at A? So you have to do a structural analysis. You have to decide where to cut the loop, which joint should have its own relative coordinate associated with, and which joint should be left alone, because this special joint, the other kind of joint, will be represented by constraints equations. Okay, so you need to do something. When programming this is a problem. I give you a mechanism, and then you are to decide where to cut it, how to create the equations. Those equations are usually created recursively. So we go from one body to another, to another, to another, and the equation grows and grows and grows. It's not for a general system, it's, let's say, a recursive process, not closed form of equations. Having said that, we move to other coordinates, which are called Cartesian coordinates. How about this? For every moving body, we can establish a local reference frame somewhere. It can be in the middle of the link here, the center of mass. Quite convenient. It could be here at joint A. It could be practically anywhere. So we take a rigid body and we establish wherever we want a local reference frame. And our generalized coordinate and our coordinates for a particular body would be position of this origin, like X and Y here, and conphi saying how this local frame associated with a body is rotated with respect to the global frame. Okay? So we establish local frames here, and it's not shown here, but something like this. Yes, we've got global frame here. There is a link with local frame here. So should go like that. Okay, so this is our local frame. That's how we measure angle. That's how we measure our R equal X1. Okay, and we can do virtually for any part wherever it is. We can establish local frame, measure the angle, measure the position, generalized coordinates of a multibody, of a single body. And this is shown here, yes? We've got 3 local reference frame associated with every single part here. And we've got a number of coordinates. First 3 are for this local frame here, yes? X1, Y1, and Phi1. I fully know what is where is located local frame here, so I know by having those coordinates, I know where the part number 1 is. X2, Y2, Phi2 for the other link here, and the same for link number 3. Altogether, quite a lot, 9 coordinates, awfully much, yeah? Apparently not very convenient, especially if you want to derive your equations on paper. But if you engage computer, maybe it's not so bad. How many constant equations do we need to derive now? We've still got 1 degree of freedom system. Now we have 9 coordinates. 8, apparently 8. Awfully much. Yes. But let's have a look at those equations. They start here, okay? We are there. xy minus r half. What does it mean? Let's have a look at both those equations together. If I move from global 0, from A here, by xy and y, x1 and y1, I will go there, yes? And if I go back with r to half of the length here projected on x and y, I will be back right here, okay? So this is an equation that in fact says there is a joint at point A. I cannot go with x1 and y1 everywhere. I can go as far as I'm allowed. I must go back using this phi angle and distance r divided by 2. Go back here. So this joint exists. Okay, the same can be done for another joint. The most important, the nicest is joint B. Let's try to draw it to make sure everyone can think about it. So that's the story. We've got first part, we've got the other part, we've got local frames here and there, and we've got somewhere here the global frame. So, and point B is here. I go from here to there. This is my x1, y1. And then I go farther here. It is r divided by 2. And projected, this is the length, yes? I need to project it. This is my phi 1. So r divided by 2 is projected on x and y. And I'm right here. Then what I can do is go to another color. I can go directly here to the frame 2, which will be x2, y2. And I can go right here, which will be, what letter is here? D, probably. It will be D divided by 2, and again, projected with minus the projected by cosine pi 2 sine pi 2. Okay? I can go that way, I can go that way, I end up with the same point B. So when I subtract from this the other way of going to point B, I will have those two equations here. So basically, those two equations express the existence of point B, of part of joint at point B. The other two equations, in the same way, by going from A straight to origin of second local frame and going farther to point C, and then by going from A to local frame of part 3 and going from local frame of part 3 to point C, those equations express existence of joint if point C, and the last two equations existence of joint at point D. So we've got a lot of equations, but in fact, those equations are closed form equations. They involve only coordinates of two parts that are involved in building the kinematic joint. Yes? Does not really matter how many more parts do we have. Our equations would not change. For point C, equations involve only second and third coordinates. No more, because second part and third part create joint and C. So those equations can be programmed in a closed form, and they do not respond to change in the system. I mean, if we add more bodies to our system, nothing changes with our equation. Yes? Well, in the joint is always created by two parts. Okay, the joints can coincide. If there is a third body, you must decide to which of the first two it is connected. There is no such a thing like a joint composed of more than two bodies, basically. Okay, so it will be a separate joint, and we will use absolute coordinates, or these Cartesian coordinates, which are sometimes called absolute coordinates, to express the existence of joint. Okay, so let's summarize. What do we see here? A lot of coordinates, not good. A lot of constant equations, not good. But are there any positives? Yes, they are. Firstly, those equations would never be more complicated. There are like they are, closed form formulas can be directly used in a computer just to create those equations. Not much structural analysis is needed. We do not decide where do we cut our loop. Cut it everywhere. Every single joint is treated the same way. Every single joint is represented by subset of constraint equations. Completely different than in the previous case, yes? Just joint D was singled out from all joints, other joints, and constant equations were associated with joint D only. The other joints were indirectly represented by having joint coordinates associated with them. Okay, but now here the situation is much more clear. I take the mechanism, I in fact take individual bodies and create equations, single equations, separate equations for every joint here. So it is much more systematic. I do not need any recursive procedures. I just take one part, the other part. If they create a joint, I may forget about all other parts. Just two sets of coordinates, subsets of coordinates are used in those equations. And that is why those Cartesian coordinates are so frequently used. When it goes to coding this, to writing a multi-body program, it is quite easy to do it when you use Cartesian coordinates. When we've got some course which takes 30 hours or something like this of multi-body dynamics, and students at the end are required to create their own multi-body program in MATLAB. In absolute, in Cartesian coordinates, because it's extremely easy. It takes few hours to create your own simplified but still working multi-body code for kinematics and the dynamics. If the students were supposed to create it in joint coordinates, well, they would need much more time and much more frustration. Okay, so those coordinates, the choice of coordinates affects strongly how it is, affects strongly the easy. I lost my word. It depends on coordinates whether it's easy or not to create a program. But how about efficiency? What do you think about efficiency? If we've got 3 coordinates and 2 equations, or 9 coordinates and 8 constant equations, which approach will be more efficient? Usually, yes, but not significantly. The problem is, well, if you go further, if you go to velocities, accelerations, you differentiate those equations. Okay, and having Cartesian coordinates with closed form constant equations, you also have very simple closed form equations for the derivatives, for the Jacobian matrix. Moreover, if you look at those equations, I stress this, that just part number 2 and part number 3 are involved. It doesn't matter how many parts do we have here. If we go back to relative coordinates, you see in constant equations all coordinates. If there are more bodies, you will see more coordinates in your equations, which means that in the Jacobian matrix, you will have a dense matrix. Yes, every single column will be filled with some derivatives of constants. That's not the case in absolute coordinates, because if you take derivative of this first equation here with respect to coordinates of body 3, there is 0, 0, and 0. And the more bodies you do have in your system, the more zeros you have in the Jacobian matrix, because that's a rule. In absolute coordinates, your equations, your constant equations involve just equations of part number 1 and part number 2, no more parts. So you have hundreds of parts, and in the Jacobian matrix, you will have 0, 0, 0, zeros, and just somewhere something that is non-zero. And you can use sparse matrix algebra for computation. So the matrices are huge, but they are not dense, they are very sparse. Well, have you had a course in finite element methods or something like this in structural dynamics? Well, they do have large matrices, yes? Like million by million. Of course, they never store it. They know that they are so sparse. Yes, non-zero elements are located at very precisely known places, and those sparse matrix algebra helps to solve this huge problem. The same can be done here. So at the end, if you do a professional program, yes, probably relative joint coordinates would be a bit more effective in computations, but a bit, not dramatically. Yes, the difference here is 3 versus 9, or 2 equations versus 8 equations. The difference is dramatic, but not at the end of the day. When you do all your computations, when you skillfully use sparse matrix algebra, you end up with almost equally efficient programs. And programming in Cartesian coordinates is much more easy. So basically, seminal books in multibody dynamics by Nikraves, by Haug, they all use those absolute Cartesian coordinates because it's a good idea, because they are very nice to do the job required. Okay, so that's the summary of set of coordinate choice. If we look at coordinates like minimum coordinates, of course, the number of coordinates is minimum, the number of equations is minimum. there are no there are no constraints, but derivation of all equations is very difficult. Development of program, creating a program is also very difficult. Relative coordinates are much more easier than those minimum coordinates, but much more complicated than Cartesian coordinates. So as you can see, efficiency, Cartesians are not so efficient, but the difference is not so dramatic. This part is very important. Cartesian coordinates are easy. We have a uniform approach to everything. Every joint is represented by separate set of constraints. Every single part has its own set of coordinates. So it is very regular, very easy to automate, and very useful that way. Okay. To finish this, there are also very nice coordinates called natural coordinates. You may have encountered them somewhere. They were developed in 80s and 20s in Spain by Garcia de Jalón and Eduardo Bayo. And in fact, they are still being used in some academic especially in academic studies, not necessarily in general purpose multi-body codes, but you can find also so-called natural coordinates where some crucial points of mechanism, like points at which link joints are located, are used as coordinates. There are even more absolute natural coordinates than absolute coordinates, but equations are usually much more simpler because they are linear or quadratic equations, no sines, no cosines, or no angular quantities usually, which is quite nice feature. Okay, so if we are going to create a general purpose program, well, we have to choose coordinates that we want to use within this program. For the beginners, at least, absolute coordinates, Cartesian coordinates are strongly recommended. What such a program should do? Should accept somehow data from the users, from you. So what would be those data? How many bodies do we have? How they are connected. So what is the type of connection? Is it revolute, translational, or another joint? Where this joint is located, so some geometry. As where exactly is axis of relative rotation. That's what we need to know. If we go to dynamics, we should know where are centers of mass located, what are the tensors of inertia, and so on. And this is our duty to provide the program with some data. Usually, the professional programs have a preprocessor so that you can draw your mechanism, decide where are joints, which type of joints, and that's it. That's almost end of your job. Then the program should generate equations of motion. Of course, it's difficult to say it in a 3-hour-long lecture, but following this choice of coordinates, we can create some general forms of equations for different joints, which can be used just to create a library of joints. It's easy enough to decide, okay, I've got a revolute joint right here. I need a position of the axis with respect to one body, position of the axis with respect to the other body, and that's it. The program will be able to create constraint equations. So once the constraint equations are created, the program is going to solve them. It depends. If it's kinematics, we usually need to solve just non-linear set of equations, so the algebraic equations are being solved. If this is the dynamics, of course, we integrate some equations of motion. Well, there's a tricky way of how the constraints are included in the dynamics equations. So, because the problem is usually mixed. We have some differential equations and we have some algebraic equations due to the constraints. And we must simultaneously deal with both, and it is usually called as DAEs, differential algebraic equations, and there are special methods to solve those kinds of equations. It's a bit more difficult than solving ordinary differential equations without any constraints. Anyway, this can be done by the program itself. User is not involved in this process. That's very good because it's so easy to make a mistake. If you do something manually, you will never end up with proper solution. If you've got 4 or 5 bodies, you may forget about writing down equations just on paper. Then the program should provide results to the user, some animation, some plots. So we've got this pre-processing phase when we create. For the beginners, they think that this is the most tedious part because it takes time to create a model. When for practitioners, once the model is created, then spend days and hours and months in analyzing this model. So if you are creating model not just for fun, just to say, okay, this course requires creating such a problem, so let's create and forget about it. If you create a model, you should remember that you will spend hours, much more hours on analyzing it. So the more effort you put in creating a easy to operate model with descriptive names, with clear structure, the better. Every minute spent on creating a good model will return multiplicated when you are analyzing the model, when you can easily access the result and so on. So basically, we've got pre-processing, then we've got this part when we solve equations that it is done by the machine itself. And then there is a post-processing when we can observe the results, calculate forces, calculated forces, distances, velocities, accelerations, whatever we want to see. In the preprocessor, we just look how our mechanism behaves. Okay, so this is more or less all about this introduction to multibody dynamics, as we decided as I learned during the break, you are far, far away from this, so more involved courses are done by you. Okay, geometric vector. That's what I see here. Probably it's again something that you all know. The difference between geometric vectors, basically arrows, and algebraic vector, columns of numbers. Well, we can use notation like here with arrow over the letter, which is nice. But for more complicated systems with many degrees of freedom, with many bodies, with complicated structure, not so easy to use, and especially this notation, this pure geometrical notation, is difficult to be easily transferred to the computer program. So this algebraic notation, which I'm going to talk about, is much more easier to deal with complicated multi-body system. So what is a magnitude? What is a unit vector? What is direction? Probably it's already known, so I will not spend much time on this slide. Basic operations like adding, multiplying by a scalar are all known. You of course know that there are some useful products like scalar product here, dot product, used to calculate many important physical quantities like work, for example. Force multiplied by displacement equals work, and this multiplication is a scalar multiplication. So we take two vector and we obtain a number, a scalar. Of course, you know that if two vectors are orthogonal, their scalar product is zero. You know that we can calculate this scalar value by taking the length of two vectors, multiplying them with a cosine between them, and that's the scalar product. And this cosine decides that if the angle is right angle, the cosine is zero. So if the vectors are perpendicular, their scalar product is zero. That's more or less what is shown in this slide here. The other important product is cross product. So we take a vector, we take another vector, and we obtain yet another vector perpendicular to the previous ones. Right-hand rule is accepted. Yes. Also, like 100 years ago, some books were with left hand, another with right hand coordinate systems. Now, commonly used is this right hand coordinate system. So if you multiply, if you take a vector product, cross product of A times B, you rotate A towards B and use the proper direction shown here. No issues, yes, more or less how to calculate a cross product. So I think there is no need to spend more time on this. Well, basically what we can do with arrows, we can do with our numbers. In our notation, a vector would be a column of, well, in planar system 2, in 3D system of 3 numbers, X, Y, and Z components of the vector. Yeah. Well, it's always a problem if you don't have 3D of the, you can imagine axis going towards you or back. Okay, so once we accept X, Y, and Z axis to be right-hand axis, so if X is here, Y is here, Z is there, well, it's easier. I teach robotics in my university sometimes, and if I want to make a drawing not ambiguous, so whether is it towards you or back to the screen, if there is an axis pointed, I just mark X, Y, and Z axis and say, remember, all our frames are right-hand Cartesian frames. So if you do not know what I meant drawing this planar picture of three-dimensional stuff, if you add X, Y, and Z, you can immediately explain whether a line is towards you or toward the back of the screen. Okay, is it okay? Probably. I suppose it's taken from some textbooks, but okay. So what we usually do when we use computer methods in mechanics, we use this algebraic representation of a vector. So vector is basically a column of a column matrix. Of course, not every quantity that can be put in a column is a vector in this sense of, well, you can add vectors some way. So if you put into those columns displacement along X, Y, and Z, Okay, displacement is a proper vector, so you can, if you have first displacement, another displacement, you can add them in an arbitrary order and so on. Sometimes you can put three numbers that do not form a proper vector, like Euler angles. Are you familiar with this? Okay, Euler angles are not along x, y, and z. They are along some skew axis. Not the same. Well, you cannot simply take one set of Euler angles and then add the other set of Euler angles and say, okay, my combined rotation is alpha 1 plus beta 1, beta 1 plus beta 2. No, it does not work this way. Okay, so that's it. So not every three numbers taken one under another can be interpreted as the vectors that we know from classic mechanics, as those arrows on the top. Okay, so let's move off with this. Our important all features like multiplying by scalar, like adding, work very good with algebraic vector, but everything that is expressed by a scalar product now is expressed by this. A transposed multiplied by B, the result is what it should be. But if we take physics and we are using those algebraic vector notation, everywhere we meet dot product, we change to something like this. A transpose multiplied by B. Then if we create a skew symmetric matrix like this associated with vector A, we can do this matrix by vector multiplication, which is an equivalent of a cross product. So again, whenever we need to calculate a cross product, we want to calculate a moment of force. Yes. We take this and we went up with proper values of C vector, which is a cross product of A and B. Okay, so in multi-body textbooks, you will see usually this approach right here. Okay, by this, that's all about the vectors. Okay. And I see that there is another hour just passed. So before starting the third part, let's have another 5 minutes just to move a bit, to drink something, to check emails or something like this. So 11:05 will be okay? Okay. So.
And we do the same as before, because one thing I realized is this file is not made for anything more complex than 2 beams.
Yeah, that's true. I mean,
I tried to edit it now, but it can't read my like this thing. No matter, like I tried to just select 5 bodies, but apparently there's something that just can't read. I tried to like edit the mesh texture head. But it still says like no.
I mean, you can talk to the federal on these to don't make the big decisions and just do the things that need to be done. I mean, our intention was basically not planetary here. Just really like videos. I mean, if you watch the videos, it's just mainly like
That's the focus like I was expecting, because she said something a real thing, like something more complex, and I was like, okay. Well, project 1 was simple, so we can project 2 is something more complex. Suddenly I watched the videos, but I constantly had something more complex for like after project 1 of mine. Then it's like 2 beams.
I really like to be something more complex, like maybe just like the light over there. So you just imagine the light is 1 beam and it's heavy part of it. That's basically like really all that needed was necessary, because really for the part 2 of the project, it's not really the analysis that's anymore the focus. There's literally just a copy paste from the project work 1. In project work 2, it's more just like kind of understanding the mindset of, like, for example, like even now we talk about how you simplify by ignoring friction or assuming this, assuming that. So it's the project work 2 is more just like, okay, so let's just say the light, it's sort of 2 beams on the top, it's just like 1 beam carrying the light. So like what kind of assumption are you gonna make? How much, like, okay, are you gonna presume that the light is just 1 equal density beams? So it's not like a separate, density on the outer parameter, empty space in the middle, and light mode. So instead of doing that, you just presume, okay, a combined density of like 6,000 kilograms per cubic. Like, it's not really complicated. I mean, this course is relatively simple according to what I worked on. So it's not really that complicated. It's just more about just giving a feel of translating something physical into simulated. I mean, the planetary gear, you could ask me if it's fine with her, but
Now we also said like that it's fine.
it's fine. Yeah, I don't like, to me personally, just working with the coursework, I'm usually notice topic 3 or 4, there's a whole bunch of issues there. It's mainly because the code package. Working with it, at least for me personally, it's very tough because there's so many, like, you go and open the folders, there's so many sub functions, a lot of them which aren't even used, but they're still there. And I'm afraid to delete them because I don't know where they're used, because some sub functions call other sub functions as well. I mean, it would take a lot more work. And also one thing, if you're gonna make 5-3 year, maybe use symmetry, so you only want to order of it. That would make testing a lot easier. It's symmetry, right? But here,
Not exactly. Oh, it's not exactly because the distance between these needs to be somewhat off because you see that interior interfacing gets one thing I realized. I mean, let's talk also because actually it's like this is 67 years, this is 26, this is 15.
well, yeah, I mean, again, this could be another thing where you just, say that you're simplifying it in this symmetric gear. So then you can just model a quarter of it and just explain in the report. And it should still, like, it's not really the realism and the results, it's more just the reasoning and the understanding of why you're making certain assumptions. So in that sense, if this works, it shouldn't really take too long. If this works, you can just stick with it, but not like this, I don't know, this code package. If you can figure it out, you can decode it, work with it, that's fine, but I didn't have the energy, so I just began trying to get the ANSYS model transfer from ANSYS to MATLAB to me and give them 2 weeks. Because the professor that created this code package is like, he disappeared, like, I think 3 years ago. So you just have to decode what's there, and sometimes tough to find what information the code package is actually using and what information is given. But yeah, you can try. I don't know how it will go. And really, when it comes to the system that complicated, unfortunately, I'm not as used to it in this thing.
I'm probably just asked if we can grow away. If you already said like actually you're only supposed to do 2 analysis of like this kind. So I think she was only some of the price that we actually had like the MATLAB still in there. So actually I might just ask if you can throw away the MATLAB thing and just do like this one and be like what?
So, well, I don't know if maybe you change that, but I remember correctly what we discussed is you would do the analysis of the MATLAB code, and that would give you like a certain, mode shape, certain frequency for the mode shape. And then you can also do a modal analysis in ANSYS and things like comparative analysis. So how the results differ and why they differ, if they differ, things like that. So it's more in that sense. I think that's what we have discussed, but I don't really change something that would help you so.
So you can just provide a body about this.
Yeah, you can just add first. I mean, the deadline for some of the things about has come, right? Yes, we have time to
I don't like it. I mean, it looks so fine.
It looks unfortunately, the code patch is tying to the capable handlings of that contract. There are the newer versions of the religion that compare action dynamic scores. Maybe those could handle it, but this one, I'm not sure.
Okay, shall we start over? Well, I see all those basic concepts were already used in my talk today. So probably this slide is a bit misplaced. Degrees of freedom, kinematic chain, joint, rigid body. Okay, so let's move on. The same picture we were already discussing. We see easily those rigid bodies here. Yes, we can neglect deflections, and joints are placed between or even created. Joint is a connection of two bodies that allows some relative motion. So in fact, you need parts to create a joint. Joint without parts does not exist. Joint is just a connection of two parts. So that is why when you are using a multibody dynamics software, you create joints, you create parts, then you create joints. You can do it another way because you need parts to create joints. Okay, so what is kinematic chain? You probably know if you take several joints connected by several parts connected by joints, it creates a kinematic chain which can be open like pendulum, double pendulum, triple pendulum, or closed like a 4-bar mechanism or slider crank mechanism. The point is here is the basis, and the basis is also here. So this is a closed loop, so you can walk around the whole mechanism. And in the open loop chain, you will go to the end, and no way to go further. You will find that. Okay, so Cartesian coordinates needs again. So we've got a local frame. Okay, I was trying to depict it by words. Now we've got a picture. Yes, there is a body. There is a local frame associated with this body, rigidly connected to a rigid body. A point S is known for the local observer as by vector S, with coordinates measured in this xy, yy, zy, x1, y1, and z1 frame. Okay, I see that, well, picture is three-dimensional, text is two-dimensional. If you think about planar system, you've got just x and y axis, and the vector pointing from global reference frame to the local reference frame, which is Ri here, this blue vector here, has just two components, x and y, with index I, if body number is I. And similarly, we've got just one angle here, which would be phi with index I. In the three-dimensional case, you will probably have here a bunch of angles like Euler angles, or sometimes you use Euler parameters, which makes even 4 quantities, but that's probably out of the scope of this lecture. So in a planar case, we've got 2 degrees of freedom associated with position, 1 degree of freedom associated with rotation. Of course, it's just an interpretation. Rigid body in a planar system just has 3 degrees of freedom. We can imagine this as a translation and rotation, but anyway, there are other ways to show that there are 3 degrees of freedom, and that's it. You can select 2 points two different points of a body, take three coordinates, linear coordinates of one, three coordinates of another, which is all together, excuse me, in two-dimensional case, two coordinates of one point, two coordinates of the other point, which makes altogether four coordinates. But there is this distance between one and another point, which is a constraint. So effectively, you've got three coordinates that can be freely chosen, and the fourth can be calculated. So you do not really have to think about rotations. That's what they do with natural coordinates. They just select points on bodies. They do not think about rotations, which means in their constant equations, there are no angular quantities, there are no sines, cosines, which makes those constraints quite easier. So that is why they invented the natural coordinates. Okay, so but back to Cartesian coordinates, we have two linear coordinates, one rotational coordinates, angular coordinate, altogether three coordinates to describe the position of a system. Now let's try to do something. This dash over the symbol S means that coordinates of vector S were measured by the guy established here on local reference frame. So in the local frame, coordinates are signalized by this dash over S. If I want to calculate position of point S with respect to the global observer here, global reference frame, which is this red vector R, RS here, what should I do? What can I do? I can go from here to the local reference frame, which is Ri, and then add vector S. The thing is, I need to add this vector S expressed in the same coordinates. Otherwise, it does not make sense. Yes, to add coordinates expressed in two different reference frames. So I need a transformation matrix here, which basically says how axes of local reference frame project onto axis of the global reference frame. So this transformation matrix helps to recalculate coordinates of vector S from local frame to the global frame. Once they are transformed, we can add them because all coordinates are now expressed in the same global frame. And that's the point. When you are using Cartesian coordinates, we try to express everything in the same global frame connected to basis of the mechanism usually, and in dynamics it's usually an inertial system with respect to which the Newton laws are executed. You probably have seen somewhere this transformation matrix, direction cosine matrix, it's also called. So if we look deeply into this equation, you can see all components here. And of course, you know that inverse of this matrix is just a transpose because it's an orthogonal matrix. The same is in 3D. So those matrices are orthogonal, which is depicted here by this red T, which is placed when -1 in a general case should be placed. But for orthogonal matrices, it's much more easy to calculate the inverse because it's just a transposition. So this is the basic equation of transforming, in fact, locally observed coordinates of point S to the point of view of the global observer here. Okay, now there is an example of a mechanism. It's still a slider crank mechanism, I suppose. 1, 2, 3 bodies here. And yes, what is shown here is that with global with absolute Cartesian coordinates. In fact, when analyzing mechanisms, we usually can forget about most of the mechanisms. What is done here? This part in the middle with point B here is part number 3, and we know everything about part number 3. We know its position, its global position, R3 vector is given, and the angle shown here, maybe I should make it larger. No, yeah, it's, sorry, slowly response. No, I was trying to make it larger, but I'm not really able to. Okay, this, sorry. Yeah, now I'm not touching the keyboard. The computer knows better. Ah, that's the reason. My battery just ran off. Okay. Sorry for that. Now it should respond more reasonably. Let's go back to the example. What this example is showing is that we probably know nothing about first part here, about second part here, the slider. We just know the position and orientation of part 3 here, which is completely enough to calculate position of point B with respect to the global reference frame, provided that we know the position of point B with respect to the local reference frame. But in a rigid body, we always do. Shape distances is not a mystery for us. We know how large this part is, so we know exactly where every single point is located when observed from the local reference frame. And the beauty of this is that the local reference frame coordinates of any point belonging to the part do not change over time. The mechanism moves, the part moves as a whole. But for the local reference frame, all remains constant. Nothing changes. So, knowing the position of point B with respect to the local reference frame, we can use the equation from the previous slide just to calculate position of B in the global reference frame. And as you can see, this is done here in 2 steps. In the first step, we just change the local coordinates into the global coordinates by using the direction cosine matrix, which depends on phi angle here, because this angle decides how one frame projects on the other frame. So the coordinates which in local frame are -1.8 and 1.3, when projected onto x and y of global frame, are the following: -0.72 and 2.1. And now I can add this to vector R3, which is given here. After that, I see the global position here. Nothing special. The one thing worth stressing is that having absolute coordinates, I do not care about remaining bodies here. It would be completely different in the case of joint relative coordinates, because I would have to start somewhere from the basis of mechanism and go part by part up to the part with point B. Okay, so all parts in a way would be involved. Now it's not the case. We have just calculated point B without knowing a thing about the other parts in the in the system. Okay, another mechanism. It's so-called quick return mechanism. When this crank rotates with a constant velocity, this slider here goes quite slowly one way and quite quickly backward. For some machines, it's useful when you are taking out the layers of surface. So you go slowly when cutting the surface, then you go back and you take another cut, and you go back fast and you go back. So this is a fast return mechanism. It works like it works because the dimensions are properly selected. So this would be if you were to create this mechanism that slowly one way, fast backward, slowly one way, fast backward. You could use the multi-body code just to decide what are the distances, what are the lengths, and so on. So this quick return mechanism, if we look at it, it's a nice planar multi-body system. It has how many? 5 rigid bodies, it says. 1 here, this crank, 2, this slider here, 3, this rod here, 4, this coupler here, and 5, the slider here. Ground part is always, not always, but usually 0. Okay, so and we usually do not count the ground part because it does not move. So we are calculating just moving parts. What we what we do have here, we've got a number of revolute joints. 1 here, 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 there. So between ground and 1, between part 1 and part 2, between part 3 and ground, and so on and so on. Every single joint is created by 2 parts, including sometimes the ground part. We also have here 2 translational joints. There is a slider here moving along this rod, and there is a slider here moving left and right. This is the part that it quickly returns in this mechanism. So we can draw the mechanism like here, we can draw the mechanism like here. It's all the same. The structure is depicted somehow. This balloon-like mechanism shows that for some analysis, the exact shapes of the mechanism are not really important, but I would prefer this mechanism because it's, you just look at this and know how it moves. To understand from this drawing how this mechanism moves, if I would hide this part, it would be a bit more complicated. Yes, to learn that okay, number 2 is going along this line. But it's just our choice how we present the mechanism for ourselves. Okay, so let's try to create in some organized manner equations that describe joints. We've got revolute joints, we've got translational joints. Let's try to create them. So that's the story that I was trying to show you there because I have forgotten. I just yesterday obtained those slides, so I feel excused for this. So the story of telling that 2 parts I and J are connected by revolute joint at point P goes like this. I can go to the point P always by going to the local frame of part I and going further using this constant in the local frame vector up to point P where the axis is located. At any moment when the mechanism moves, I can go to point P and calculate its position. So this calculation would be, I take Ri and then Si expressed in the same local, in the same global frame. What I can do also is go to the point P, this time point P associated on body J, like this, to the local frame and by S here. And the thing is, as long as this revolute join exists, point P on the I part and point P on the J part should coincide, which means if I go using this upper way, I go there. If I go using this lower way, I go to exactly the same position. So if I subtract one vector from another, I should obtain 0 because the difference is in position of point P taken from the left side or from the right side is 0, basically. So that's what it says here. Ri plus Sp, this is this way, minus this way, altogether 0. So that's it. As you can see, we can do it for any revolute join in planar case. All we need to know is those two vectors, SIP, SJP, showing where in the local frame is the revolute, where is the axis of revolution located. That's it. So to fully describe, when you create a program for automatic kinematics and dynamics of the multibody system, you just say, okay, I've got a revolute joint between I and J body, where on body I it's SIP vector, on body J it's SJP vector. That's all. Those quantities you need to send to the program. Then the program is going to create this constraint equation. All other quantities are, like in R here, there are Cartesian coordinates. In transformation matrix, that is phi coordinate again. Okay, so these are constraints. Phi is hidden here and phi j is hidden here. X and y I, x, oops, sorry, x and y j are here. So this is how we created the constraint equation in a very general form. It can be used for any revolute joint in this mechanism and for any revolute joint in other mechanisms as well. After multiplying, so after substituting formulas for AI, we can do it like this, which is not very nice. Often we just stay with this matrix vector notation and let computer do this, because there is no clear reason for doing this, for making those calculations. We can stay with previous form of matrix times vector plus another vector minus matrix times another vector. So that's it. Okay, we clearly see that revolute joint takes out 2 degrees of freedom, which is true. Yes, generally revolute, a planar body has 3 degrees of freedom, but if it is pinned by a revolute joint, it can only rotate. So 2 degrees of freedom are lost, 1 remains. Revolute joint takes out 2 degrees of freedom, which means we need 2 constraint equations. They are right here. How about translational joint? Well, it's not that easy, but it's still not very complicated. Again, translational joint should take out 2 degrees of freedom. So we need 2 equations, 2 constraint equations. So let's have a look at the first equation, which says that 3 points Qi, Pi, and Pj are always in line, which means, let's have a careful look at those indices. This is body I. On this body, I've got point Qi and Pi, and those 2 points are specially selected. They are selected to be on the line of translation, okay? And there is one more point Pj, this time associated with part J. And I say this point J should be in line with Q and P with index I. Okay, so this particular point, where is it? Pj should move along this axis. Again, I need to select it carefully. It cannot be arbitrary point. It must be a point located on this axis of translation. What does it mean? It means that if I take a unit vector n, which is perpendicular to Q and P, okay, some equations are missing. The crucial point here is what is D here? Oh yeah, D is shown here. So from Pi to Pj, I can create a vector D. Okay, and n is a vector a unit vector perpendicular to this axis of motion. So is it true that this vector n and this vector D should be perpendicular as long as point Pj moves along this line? Yes, that's true. So this is it. It's a one constraint only, scalar constraint, because it's a scalar product n transposed with D. Okay, that's not enough. Okay, because having point Pj on this line, that's not enough, because the whole part J could rotate around point Pj. Yes, with just this constraint here, we enforced orthogonality of D and N. But if we rotate part J around Pj, well, something is wrong. Yes, the translational joint does not work. But if we add another constraint, which basically says that relative orientation of one body with respect to another does not change, rotation is not allowed, this would make a complete description of translational joint. Yes. This means here at the very beginning, before motion, the difference of orientation of J frame and I frame was this: phi I0 minus phi J0. And this distance must remain constant. So if the system rotates, both parts should rotate the same way, because relative rotation is not allowed. So the difference between actual phi I and phi J must be constant, must be always equal to this original distance. That's the idea behind the second equation here. So again, we've got two scalar constraint equations combined to to create two constants describing translational joint. Okay, so more or less we are done with creating two typical constant equations for revolute and translational joints. Another thing is which points are important, because those important points are points that you need to provide for a multi-body generalized program. Yes, so for revolute joint, as it says here, we need a local coordinates of point A here. Well, we discussed it when creating the constant equations. We need to know where for this observer here is point A, and where for observer located on the other part is point A. Coordinates of those points are constant in respective local frames. So you take them, measure them once, put them to the program, and you are done. Program should work with them. For translational joints, well, what we need is, well, there is a bunch of possibilities. You can just take coordinates of one point and the normal vector coordinates of another point, like point pi, pj, and normal vector coordinates should be enough, yes, for this joint here. If we know coordinates of n, then to calculate d, which is from pi to pj, we need coordinates of pi and pj, local coordinates. We'll be able to calculate d. So those geometric quantities should be provided for the program that we are using. Okay. Mm-hmm. Okay, so now there is a note of simplifying some constraints. It's always doable. If we care, we can simplify our equations by taking into account that, for example, example is given here, some coordinates never change. Okay, if we look at slider 3 here, if we establish a local frame in the middle of this slider, it can go up and down, up and down. Of course, by creating equations of constant equations for translational joint here, we would somehow say within those equations that x component of the local frame here does not change, remains zero. Yes, goes up and down. It means y can change, local y3 can change, x3 cannot change. So we've got basically two options. Neglect this fact, so use x3 coordinate as a component of our vector of coordinates and associate it with some constraints saying x3 constantly remains zero, or do some pre-processing, which means crossing out x3 coordinate, crossing it out from our set of coordinates because it's constantly equal zero, and crossing out one equation. So by doing this pre-processing, we can sometimes reduce the number of coordinates and reduce the number of constraints. For special cases like here, yes, it can be done, but well, we lose generality doing this, yes, because we have to carefully examine. If we are using a general purpose program, probably the program would simply generate constraints for this translational joint. Those constraints would block the horizontal motion of the local frame. So we would have horizontal coordinate and appropriate constraints, and we will live with this. If preparing a specially designed program, yes, we can do something like this, reduce the number of coordinates in the pre-processing phase. And this is often done, especially in those natural coordinates, because, well, that's the special set here. In absolute coordinates, we can do this to implement it in a general purpose program. I don't know if the profits are worth introducing such complications to the program to analyze constants, because the thing is, you have to detect constants that say that some coordinate remains constant. If you have such a constraint, we can cross out this constant, we can cross out this coordinate. Sometimes you can do this, but it requires another effort. Without this, your program will still work using a bit more coordinates, using a bit more constraints, but not losing the generality, not requiring taking and magnifying glass and looking for special cases of constant coordinates. Okay, this follows, yes, that some constraints can be even simplified. There are some constraints that constrain just 1 degree of freedom. In three-dimensional case, there are constraints that constrain more than 3. Okay, another important thing, just for the remaining 20 minutes, is driving constraints, in fact. Usually, when analyzing motion, driving constraints is a term from kinematics, pure kinematics. If we want to analyze motion without looking at forces and masses, we can do it, but our motion must be somehow defined. If we just draw a 4-bar mechanism or a standard crank mechanism, it still has 1 degree of freedom. So there is a lot of possibilities how this mechanism can be located, how this position in time could change. We need to know something about the mechanism. So the pure kinematic analysis requires creating so-called driving constraints. Usually we simply know that something is moving somehow. In this quick return mechanism, we know that the motor is making the crank to rotate with a constant angular velocity. Yes. What we may ask, how, due to this input motion, the output motion looks like. That's the idea behind the driving constraints. So some constraints are expressing our knowledge how some part of the mechanism moves, or it can express our requirement. We can kinematically analyze a robot. So I can impose a constraint saying, okay, the end effector of a robot should follow this particular trajectory. Okay, like this. I need to know how should I operate with my motors, how should I move joints of the robot to obtain this given trajectory. So driving constraints define motion. They say the motion is like this, the crank is rotating, or the end effector is following a prescribed path, prescribed trajectory. Some part of motion is, so we know something about motion. We need to know more. So in the example in the picture, we know omega, we know how crank is rotating. This is a driving link. We need to know how the slider moves. Okay, so the kinematics consists in finding motion which results through finding the motion of the whole mechanism which results from information about some individual motion of a part or something like that. Okay, so in those driving constraints, usually there is an explicit function of time, like here, yes, that angle here is phi 0 plus omega multiplied by time t, which means constant rotation with velocity omega. And then what we can do, having our constraints describing the kinematic structure. So far, we were talking about, for example, 4-bar mechanism. Our 8 equations, 8 constant equations, just describe the kinematic structure, allowed for motion, but the motion was unknown. If we add information required about motion, we add the one more equation. Yes, for 4-bar mechanism, we've got 9 coordinates. We've got 8 constraints that describe the kinematic structure, the constraints representing kinematic joints, and one more, just one more, because we've got just 1 degree of freedom, one more information in the form of driving constraints CD here, usually a explicit form of time. If we add this this 9th equation, we've got, that's interesting. 9 equations with 9 coordinates, which means as many equations as unknowns. The kinematic problem is then formulated, yes? We've got 9 unknowns, 9 equations. What about time? Is a time an unknown here? What is a time? It's just a parameter, yes? We know the time. For time 0, the crank is in this position, okay? Calculate the rest. And for time 0, velocity is given, so calculate all velocities of interest. For time equals 0, crank is in this position, velocity is known, acceleration is known, calculate all accelerations of interest, yes? Then we go a bit further. Time 0 plus dt, okay? In the kinematics analysis, time is discrete. Given time, another given time, another given time, we can take the points in time as close one to another as we want to, but it's always a discrete point. In fact, after some time, the crank is not in this position, it's in that position, and the velocity is different and the acceleration is different, but still given. In fact, it's not very important what was a second before. Yes, every problem of kinematics is in a given point of time. So in our equations combined of C and CD here, time is a given parameter for a given time. The driving constraints say something different. Yes, there is a different position. If we differentiate driving constraints, which we can do, we will see driving constraints from velocities. If we differentiate it once again, we'll have driving constraints for acceleration. So by providing function of time, we already provide all other derivatives of velocities, accelerations. If we want more, there is more, yes, like third derivative and so on. So for a given time, we can solve a system of equations. Well, I think see that the details are missing, but this is the formulation of velocity problem after differentiating constraints at the position level, both those material constraints that depict joints and the driving constraints that describe our knowledge about motion of the mechanism. If we differentiate once, we see a set of linear equations with respect to q dot. That's what I started with. Now we've got proof in equations. If we differentiate it once again, we've got a linear equation with respect to acceleration. Okay, so of course the toughest part is to solve those equations combined at the position level, because that's the only moment at which we have to solve nonlinear equations. But still, there are algebraic equations. Okay, we do not have to integrate anything. We just substitute given time here and solve for our unknowns. Once we calculate positions, we can calculate velocities. Once we calculate velocities, we can calculate accelerations. We cannot reverse this order because, as you can see, those matrices here are given for special known position. We must know position. Velocities must be known here to calculate, to solve this set of equations. So it's always this order: positions, velocities, accelerations, and the problem is solved. Having q dot, q double dot, where q is the absolute coordinate, Cartesian coordinates vector, we can calculate position, velocities, whatever we want in the mechanism. Okay, and yes, that's for the very end of this lecture. There are some additional equations. So imagine that we managed to solve for a given time position, velocity, acceleration problem. So we do have absolute coordinates for a given time. If we are interested in a position in some point which does not coincide with the origin of local frame, because local frame position we've got already here, yes, in our vector of coordinates. But if the point is somewhere else, we can use this equation to calculate position of this point. If we take time derivative of this equation, we see formula for velocity of this point. Yes, on the right hand side, we've got only quantities that we know from solving equations from the previous slide. When we take second derivative, we have this equation here, and again, we've got here only quantities known from the solving equations from the previous two slides. Now, I don't know if you are familiar with this way of taking derivatives, that using so-called Poisson formula, you can change taking the derivative. So operation of differentiation can be replaced by multiplication of matrices. It's not very difficult to prove. So this partial derivative can be expressed like something like this. So the total derivative would be omega times a times phi dot. Quite easy to calculate. Okay, so using those formulas, you can calculate every information of interest: position, velocity, accelerations of any given point. Slide number 33 appears to be the final slide. So I managed somehow to go through Greg Orzechowski's slides. Thank you for attention, especially thank you for being here. It's much easier to talk to people than to screen. Have you ever tried? COVID was fantastic. Imagine, I sometimes joke during my lectures, and you're saying like this, you say something which is supposed to be funny, and there is blank, nothing. After a long time, someone switch off the mic and says, haha. So no joking at all, because due to this delay, it's even if they smile, the reaction is like, well, talking in a completely foreign language, and nobody understands you. So thank you guys very much for being here, and enjoy the rest of the day. I try to stop